This topic, as you might see, is a little bit, I would say, high-level topic in the sense that we are not going into deep study of any individual topic or subject, but rather an overview of these aspects of civil and structural engineering which relate to the design, construction, management of built environment, and how can we make it future-proof. So let me start with this first sort of statement that I think we all know that humanity has always been fascinated by predictions about the future. And we have seen people predicting future based on celestial movements and palm reading and so on. So we're always interested to see what's coming next. And those predictions sometimes come true, sometimes they don't. And if you look at the predictions, you will also notice that some of these predictions paint a picture of a very bleak future. And when they paint the picture of a bleak future, one of the things is obvious in such depictions that the infrastructure is all destroyed, it is in a bad shape. So the future's bleakness and the infrastructure's sort of state are interrelated somehow. So which means that the buildings, the bridges, the roads, and other things, they are considered to be part of the future reference. Another prediction which paints a bright future, you can also see there's always infrastructure, which is the focus. So when we have a bright future, we have flying cars, we have motorways like this, we have tall buildings, we have greens infrastructure, and so on. So both these future predictions or future views, bleak or bright, somehow are related to the built environment. And we as civil engineers are part of that process. So that's why, to me, future and built environment are very closely linked. Those of you who are old enough, or those who have followed this book, this was a very, I would say, important book written about the future. And it actually set up a whole cultural movement at that time called Future Shock by Alvin Toffler. And I read that early on, and when I was very young. And it was very fascinating. And in fact, this is one of the books that has become critical discussion of the future as they develop. And people have been comparing the development of the future with the predictions made in this book quite often. And they have found that a lot of predictions made by him are now becoming a reality. So future shock, as you can see, means that when the future we reach there, we always have a kind of unexpected things that we did not anticipate naturally. And in this book, he argues about there's no permanence. Everything is changing very, very quickly. It's transience, there is novelty, diversity, over choice of things. And we have seen it all. And this was written in 70. And, any place, for example, you want to buy anything, there's a whole choice and you are in a difficulty to even select simple utilitarian things. So, which means that now we have to think about how can we do something which will stand the test of time or will be relevant in future. So future-proofing terminology is becoming important on almost every discipline. And this is also now finding its way to civil engineering. So the first future-proofing can be defined in many ways, but in one way is that it's the process of anticipating the future, developing methods of minimizing the effects and shocks, stresses of the future events, and including effects of climate change, of course, which is part of the future, which is almost becoming a reality. So this future-proofing now is becoming that organizations, they always look at how they can future-proof themselves, their products, and so on. So why it has become so important now? And obviously, one is the rapid change, technological change, climate change, globalization, population expansion, demographic shifts, urbanization, where everybody's moving from the rural to urbans. Urbanization is reaching 60%, 70% rate in most countries. Economic volatility, we have all these economic crises coming every few years, every 8-10 years, we have some kind of a bubble burst. And then we have what produced these pandemics and health crises. So we can see that there is very rapidly change. These things may have happened in the past too, but the rate of happening was quite slow. In fact, if you look at the timeline, the first agricultural revolution was something like 10,000 BC. Long time ago, when people moved from being a nomad to agricultural society. The second agricultural revolution that changed the way the agriculture worked was in 1700s and 1800s, beginning of that. And then after that, suddenly we have a flurry of industrial revolution, first and second and third and fourth and fifth. Within a very short span, we have this rapidly changing industrial landscape. So you can see that for the first 12,000 years, almost nothing happened and everything was more or less stable. And future, present, and past were mostly the same. There wasn't much change expected. But in the last 350 years or 400 years, we have seen so much change that we are having a revolution every 50 years and not even smaller duration. So this accelerated rate of change is making everybody dizzy, so to speak. So now we are more worried about the future change, and anything that we do becomes irrelevant very, very quickly. So that's why the future management of the future or future proofing has become important. Those of you, young generation especially, I don't know how many of you are watching. If you watch this movie's trilogy, Back to the Future, it is actually a very interesting study of the 4 industrial revolutions, because it takes you back and forth in time, step between 1850 and 2015. And even though it's a fictional movie, but it actually captures a lot of those changes very, very appropriately. And those shots that we're talking about, these are depicted. So we can see now that the change within that short period, we have had 4 industrial revolutions. Now, how does it affect the built environment? So built environment is actually a response to population growth, to urbanization, to globalization, and so many other things. And this built environment is actually the backbone of economy and society. The development is measured by the infrastructure development, and infrastructure development sort of spurs the economic development and so on. So they are both interlinked. As you can see very well, that whenever we see any country developing, the first thing we see is infrastructure, the roads, the buildings, the bridges, the communication infrastructure, and so on. So infrastructure is kind of synonymous to economic development. So physical infrastructure, which civil engineers are kind of responsible in a significant manner, is the key. We have seen this from the historical perspective. We have always seen that whenever somebody wants to make a statement, they will build something. And we have seen it over and over and over again. And we can see now that the infrastructure development is becoming more modern, more innovative, and is changing much faster than before. Materials are changing, and the infrastructure is physical infrastructure. It supports everything that is done. Whether it's mechanical engineers, electrical engineers, communication engineers, they all need physical infrastructure. And that physical infrastructure, obviously, structural engineers have to design. So in a way, if structural engineers do not do their job well, no one else can. And so physical infrastructure supports all kinds of other development, and civil and structural engineers are responsible for designing, building, maintaining this infrastructure. So you can see from here, airports and fields and everything that you pick is all about that. And now we have this vision of the future for vertical cities, where people want to, because of the environmental and many considerations, it is seen to be better to have a vertical growth than spatial growth, because it saves a lot of space and commuting and fuel and many things. So there is a concept for as high as 4-kilometer high cities have been developed. And some of them, especially in Dubai Creek, which is under development now, is one of those projects. So obviously, when we have such rapid development, then we clearly need to make it future-proof. That means we can't build these things for just a few, 40, 50 years. It has to be a long-term endeavor. So these structures, buildings have to remain serviceable, have to remain always safe, have to be resilient, which is much larger concept than safety, have to be flexible in terms of change of the use, adaptation. They have to be adaptable with the changing times, with the environmental effects, and sustainability, of course, is the key. And most importantly, they have to be dismantleable. They have to be end of life built into the design, so that the building reaches its end of life. It can actually be dismantled properly. So now we will discuss some of these issues in a little bit detail. And if we do not think about future proofing, then we have vulnerability to climate change, high adaptation costs, disruption and downtime because of the buildings not being available for essential services, missed opportunities, and decreased competitiveness for a lot of businesses. So there's a whole danger if we do not make these structures and these buildings future-proof. Coming now to the third and important part of the discussion, which is the real focus of today's talk, is how can the structural engineering and structural engineers participate or adapt their work or modify their work or consciously include in their work the future-proofing concept. So like I mentioned, civil engineering and structural engineering is the backbone of physical infrastructure development, which means buildings, bridges, tunnels, dams, transmission towers, communication towers, power plants, expressways, industrial plants. Everything that you see around us is structural engineers and civil engineers domain. And so that is very clear that backbone of physical infrastructure is structural engineering, civil engineering, and physical infrastructure is the backbone of economy and the economic development. So we have a very important position in society, whether we recognize it or not. Unfortunately, we ourselves and public does not really recognize that as they should. So now, what can the structural engineers do? Most important, number one, is to have a resilient design. And resilient design doesn't mean safety or following the code, but it means much broader concept. And we will just discuss some of them now. And I'm sure you're already aware of them. Second one is innovative materials and techniques. And third one is also something that we will discuss today, depending on the availability of time, the integration of technology into the work that we do, into how we do it, in what we do. Technology is the key because we have these industrial revolutions rapidly happening. So if we don't bring them into our discipline, we are going to miss out. Adaptive design, like I mentioned, whatever we do, it should have the ability to change with times, with needs, with the utility. Life cycle analysis, and this is very important. We often miss that because we think about the design and we think about the construction when we are designing, but we don't think about 50 or 100 years or so on, during which time this building or the structure will be in use. And that is the real cost that we should be thinking about. But often we are concentrated or forced to concentrate on the construction cost and the design decisions that only affect that probably at the cost of the life cycle cost. So collaborative planning, work together with other disciplines. So let's go into a little bit more depth of the resilient design now. So resilient design basically means that it has to be robust over a long time, and it anticipates the potential impact of climate change and flooding and severe weather events, which are coming, as you can see, and so on. And we have to design these structures to withstand natural disasters. Let me just repeat this statement from one of our good friends, Ashraf Habibullah, and he always, in his talk, starts with that structural engineers help to preserve the past, they protect the present and build the future. So that's what our thinking should be. How can we preserve the past and while we protect the present and build for the future? And that all of it begins with the reduction in the risk for the disaster for built environment. So if you look at the disaster, it actually has, I think three key components. It's the combination of hazard, vulnerability, and exposure. Now, hazard is something that we may not have a lot of control on it. Exposure is, once again, it depends on the use of the structures, on regulations, on many things. The one thing that we, as structural engineers or civil engineers, have a control or have responsibility is about the vulnerability. So, inappropriate built environment is one of the key multiplier here, because hazard can be managed to some extent. Some hazard can be, some cannot be. And people and property which is exposed, once again, is a matter of policy and other beyond our control sometimes. But vulnerability and hazard, which combine to be risk, is something that we should think about managing. And if we can manage this, then we will have a resilient structures. So as you know, structure is basically a stepwise integration of materials which make up the cross-sections, which make up the members, which make up the structures. So whenever we design or take any decision, it must be spread across all of these 4 steps or components. So material selection or resilience at material level, at cross-section level, at member level, at connection level, at their interface, and finally at the structure level. So all of these are part of the structure, and every decision that we make must carefully be considered for each of these steps, which relate to design, construction, maintenance, and so on. Second component, obviously, is the load effects on the structures, which is external, which is the part of the. So this one actually leads to vulnerability control. And this one is the hazard side. And hazard side could have many components: dead light loads, wind load, soil pressure, seismic load, snow, thermal, temperature change, humidity, creep shrinkage, and so on. And this endless list of these hazards that our structure could be exposed to. And our challenge is to make sure that our structure has the ability to withstand or counter the effects of these hazards or load effects. So to do that, structural engineering has been evolving over time, starting with the intuitive design before the computations, before Galileo, before all those people, when we had the master builder concept. They just knew what to do. And through experience, they have learned it, the tradesmen, and they could almost always come up with some solution. And we have seen that some of the great intuitive designs have lasted centuries. But they were few in number, and they were done by rulers or people with large access to resources. Common people did not have that. But after the industrial revolutions started, then a large number of infrastructure needed to be built, and there just weren't enough master builders to do that. So engineers have to be trained and constrained by code-based design. They have to be given limits. According to one of the engineers, Hardy Cross, we had to have code-based design so we can prevent people from making big mistakes and also prevent people for making very innovative design. So it's a control on both ends. But that was not enough, because we found that it was completely putting the engineers in a box, and that didn't work when the structures that we were dealing with did not follow the code limits. Codes are not developed to handle Burj Khalifa's type of structures. They have to be done outside the code. So the performance-based design came up, and every other discipline has taken up, and now structural engineering, civil engineering is also following that. And from that, we went to consequence-based and risk-based design, and from there to resilience-based design, and then now we have the tech-assisted solutions. So we are in this ladder of evolution of the structural engineering, and especially seismic design approaches. And this is for earthquake, and also now wind is catching up. So basically, the way that we work is evolving to meet the needs of the society that is changing so quickly. So code-based design is just not enough in most cases. And now let me talk a little bit about the performance. So as you know, structure is basically a stepwise integration of materials which make up the cross-sections, which make up the members, which make up the structures. So whenever we design or take any decision, it must be spread across all of these 4 steps or components. So material selection or resilience at material level, at cross-section level, at member level, at connection level, at their interface, and finally at the structure level. So all of these are part of the structure, and every decision that we make must carefully be considered for each of these steps, which relate to design, construction, maintenance, and so on. Second component, obviously, is the load effects on the structures, which is external, which is the part of the. So this one actually leads to vulnerability control. And this one is the hazard side. And hazard side could have many components: dead light loads, wind load, soil pressure, seismic load, snow, thermal, temperature change, humidity, creep shrinkage, and so on. And this endless list of these hazards that our structure could be exposed to. And our challenge is to make sure that our structure has the ability to withstand or counter the effects of these hazards or load effects. So to do that, structural engineering has been evolving over time, starting with the intuitive design before the computations, before Galileo, before all those people, when we had the master builder concept. They just knew what to do. And through experience, they have learned it, the tradesmen, and they could almost always come up with some solution. And we have seen that some of the great intuitive designs have lasted centuries. But they were few in number, and they were done by rulers or people with large access to resources. Common people did not have that. But after the industrial revolutions started, then a large number of infrastructure needed to be built, and there just weren't enough master builders to do that. So engineers have to be trained and constrained by code-based design. They have to be given limits. According to one of the engineers, Hardy Cross, we had to have code-based design so we can prevent people from making big mistakes and also prevent people or for making very innovative design. So it's a control on both ends. But that was not enough because we found that it was completely putting the engineers in a box, and that didn't work when the structures that we were dealing with did not follow the code limits. Codes are not developed to handle Burj Khalifa's type of structures. They have to be done outside the code. So the performance-based design came up, and every other discipline has taken up, and now structural engineering, civil engineering is also following that. And from that, we went to consequence-based and risk-based design, and from there to resilience-based design, and then now we have the tech-assisted solutions. So we are in this ladder of evolution of the structural engineering, and especially seismic design approaches. And this is for earthquake, and also now wind is catching up. So basically, the way that we work is evolving to meet the needs of the society that is changing so quickly. So code-based design is just not enough in most cases. And now let me talk a little bit about performance-based design, because that is related directly to resilience. So in performance-based design, hazard and response, they fight directly and fairly to determine vulnerability. That means we don't bring the code, we take the codes out of the equation, and we let the real load facts and real capacity or real performance compare with each other. And this is done by obviously advanced nonlinear analysis, nonlinear dynamic analysis, whatever, to make sure that we remove all of the factors that we put in the codes and then try to find the real capacity or real performance of the structure compared with the as real hazard as possible. And this picture actually depicts that very clearly. On one side, we have the material. From material to behavior cross-section. From cross-section, we have member behavior. And on the other side of the equation is the hazard. And starting from, let's say, for earthquake, we're starting from ground motion to response spectrum. And then we try to bring them together at a common meeting point, which is the performance point. So now which means that by any decision that we make on the left-hand side in the change of material or the cross-section will directly reflect in the performance point shifting. And if there is a change in the hazard on the other side, seismic, earthquake, time, ground motion, response spectrum, it will also show up in the performance point. So that means we can now fine-tune the tool so that they meet exactly where we want them to meet. So this approach gives us a very good control over predicting the performance well, so that we can actually design in a more reliable manner. And we can make decisions that can then be evaluated and sort of compared between the different designs. Because if you just have code-based design, there's nothing, the performance isn't explicit. So that's a separate subject we will discuss another time, but let me move on. So design decisions in this case are explicitly linked to hazard levels and the key performance indicators. So KPIs have to be met, and the decisions have to lead towards KPI. This is common in organization. If you are working and you have a job, you have a TOR and you have KPIs. So you are expected to do something and you have to perform in return. And that's exactly what we expect the structures to do. We have the KPIs and so these are the KPIs that we have to sort of meet, which will ensure that the structures will perform properly in the future. Stability, strength, deformation, drift, ductility, energy, motion, all of that, and many other KPIs can be added. So just to give you a quick rundown of how this can be done, this is a simple pushover of a tall building where we can see as the hazard increases, we have the damage in the structure that we can capture, and then we can compare when the damage has exceeded certain limits and what kind of level of damage is acceptable and what level is not acceptable. Similarly, we can do a little bit more by using time history analysis, so we can actually do it in a dynamic, nonlinear manner, so we can capture the structure's performance more appropriately and more accurately than pushover and other static methods. So the point is that we have the tools and we have the technologies to do that at this point. And we can use these to make the structures more explicitly resilient, so to speak. So what we need is an understanding of all of that. We also need to have an agreement of the stakeholders, and we need to have the right information. We also have to have the right tools and guidelines. and we have the ability to interpret these results and determine the performance properly. And this requires a lot of patience because it's not the traditional way. So it requires for us to do the things in a very detailed manner. But once we have that, then we have the ability to now move to the next level. From performance-based design, we can move to the resilience-based design and actually ensure the resilience of not only the structure, but the community that the structure serves. For example, if it's a hospital, we know that if the hospital is damaged, it will actually immobilize the whole community during an earthquake or during a flood or whatever, because you need those essential facilities. So their performance, their resilience has to be really very high. So that's why the Resilient Building Society was formed, council was formed, just like we have the Green Building Council, we also have the Resiliency Council, and then the two sort of work in similar manner to have green buildings, which is environmental, and then resilient buildings, which is disaster resilience. So we need to have structures which are both, they both are green and resilient. So this combination now is something that is clearly indicated in the view of climate change and sustainability. We need both because each is affecting the other. And we can now relate the performance or damage or loss to the structural indicators. And we can relate that to casualties, downtime, rehab to restore the structures, and so on. And so we can have more confidence on the structure's performance as well as its resilience in the longer period of time over the life of the structure and over a range of hazards. So, which now brings us to the last step in this one, which is the future-proof design. So if we have gone through performance-based design, risk consequence, risk-based design, resilience design, then we can achieve or we can move towards the future-proof design because we have the tools and we have the indicators that can be used to evaluate or that can help to explicitly design something which we can term as future-proof. So if you look at the requirements of future-proof structure, remain accessible, serviceable, safe, resilient, flexible, adaptable, and compare it against various types of design methodologies we have, you can see clearly that the future-safe design will meet all these requirements the best, whereas the code-based design may meet some of them, but not many of them. So as we go from intuitive to future-safe or future-based design, we can meet the requirements more explicitly. There's a higher chance that we can meet those requirements. And of course, we can do this through innovative materials, use of durable materials, use of sustainable materials like recycling, adopting new types of composites and concrete, and use of new construction technologies like 3D printing and so on. So everything has to come together. It's not only the design. We also have to make sure that on the construction side, there is also a development that matches what we are evaluating. So this brings us to a very interesting question, which is the design life. Most engineers, most people think automatically that we have a design life of the structure of 50 years, 70 years, 60 years. And if you ask the engineers, can you design my structure for 100 years? Or can you explicitly tell me what is the real life of my structure? It's a very hard question to answer. And we don't know what dials we should change to change the design life of the structure. And some clients, and we have had clients who come to us, they say, we would like our structure to be designed for 150 years. And then we sit there and scratch our heads. How can we do that? Because the code, we have basically code-based design that doesn't really give us any indication or any way to evaluate this explicitly. But there are ways to do that. And without going into the detail, if I look at those, we can see that, first of all, material selection is durability, maintenance considerations, safety margins, adaptive design, protective measures, life cycle analysis, and responsive design are part of that. And most importantly, we should design the structure from the beginning to be retrofitted. This is not a word. I invented that word, retrofitability. It actually, if you look for it, you might not find it, because this is the concept that the structure, you should anticipate that in future, at some point, this structure might need to be retrofitted. And we should have the ability to do that. For example, in bridges, they design the bearings to be replaced in future. So that means the retrofitting of the bridge by replacing the bearing is part of the design. Adaptive design, the same thing. We have to make sure that the design can adapt to changing life loads, to changing. Many times the building is sold from one owner to the other and they change the use. Now it is not considered environmentally good to take a building and tear it down, because previously it was okay that you buy an old building and client would just blast it and tear it down and build a new one. Now the environmental considerations will not let them do that, because that will cause an environmental impact. So the tendency to keep the building, adapt it, build upon it, retrofit is much more now than before, because of the resources that we use to make new building are just scarce now. So life cycle analysis is very important. We have to conduct the entire life cycle from the beginning to the end. And if you look at the typical life cycle of a project, it's pretty long. It has like 30, 40 steps in there. And as structural engineers, often we are only looking at 3, 4 of them. We are not looking at the entire project life cycle. And that's where the cost saving, the durability, the future proofing, and all of that lies in all of these steps that we can look at them explicitly. Conception, planning, design, construction, operation, end of life. These are the key groups of the design life. And we are mostly considering the design portion. And during that time, we do not pay enough emphasis on the other areas, which actually cost more, both in terms of money and environment. So let's take a look at the basic design life. Let's say 50 years, X number of years. And these numbers are, there's no real numerical number. I'm just giving a conceptual idea on how the design life or the structure's life can be changed or enhanced. So we have a basic life. Then if we have better maintenance, the life can be improved, because if the structure is going to degrade badly without maintenance, if you maintain it, the life will be increased. That is obvious. That's the first step that we could do. Second one is improved durability. Concrete cover is increased, concrete strength may be increased, and you have all the durability consideration. The structural life can be extended by improved durability. Durability consideration. Next is increased factor of safety, low stress levels. So which means if you do that, your structure is likely to have a longer life, because the stress cycles, fatigue, and other things will not damage the structure as much as otherwise if it is designed to the extreme. Repair, restore, will be refurbished. And if we do see damage, and if it can be repaired or restored or refurbished, then you can extend the life by another 10, 15 or X number of years. And finally, we also have the retrofit that we can then simply do a complete strengthening and change the entire structure, give it a new life. So all of these steps can change the basic design life to double or triple than the originally conceived. Then we have explicit design for extended life, which is considering a little bit more than that one. We even modify the load factors. We modify the hazard levels for the return period of earthquake. Instead of being 450 years or 2,500 years, we consider a longer period. For the wind return period being 1,700 or 1,000 years, we consider 2,500 years. So we change the return periods of the loads, and we design for the extended life. But no matter what, there is definitely still going to be an end of life. So we must also design for that as part of the future proofing, that whenever the structure comes to the end of its life, we should be able to bring it down properly. And that is the design consideration for that one. And I'm just giving some of them because we have more material to cover. So I can share this presentation with you later, that what are the things that we could do for considering the end of life of structures. Then collaborative planning is very important these days. And we have to work with the client, we have to work with the architects, with the other people, site-specific consultant, geotech. So this is just one example that we have got to make sure that we have during this process, we have to engage more stakeholders. We cannot do it in isolation, because structure is part of a bigger ecosystem. So if we are going to make some decisions, other people have to also be involved in that decision making and have to participate in that. So last part of the talk is about emerging technologies and structural engineering. And this is another part of the future proofing, not only of the structures, but also our own work. Because if as structural engineers, we cannot keep up with the emerging technologies or incorporate them into the work, we will be left behind. We'll be lagging behind other disciplines. And we have seen so many times disruptions coming to organizations, to disciplines disappearing very quickly. So we have to be conscious that these emerging technologies should help our work and also help the structures and the built environment that we actually make. So there is a paradigm shift in terms of the computers or the computing these days. In the beginning, when we started using computers, I remember writing programs to automate things we were doing. We were doing something by hand and we wrote a program to make it faster. So that was it was considered very smart that, oh, I can now do it faster. I can do more. First frame analysis program was amazing because it could do the moment distribution or whatever, or a matrix analysis very fast. But now it's not the case. Now we have to develop the process that are based on computing technologies. We have to reverse. We cannot just keep doing the things we were doing earlier and automate them. We have to do things differently because we have automation. And that paradigm shift is what we need to recognize. And purpose of technology should be very clear. Streamlining and automating the process, enhancing communication and collaboration, enabling data-driven decision-making, and empowering innovation and creativity. So that is the underlying use of technology or technology applications. So these technology or software should basically help us do things better in the end. And if you look at that technology applications in our structural design process and look at some of the technologies, for example, AI, data analytics, virtual reality, IoT, blockchain, robotics, drones, and so on, and we can see that they are quite relevant in some parts of our work and not relevant in some parts. So this relevance matrix roughly tells us where we can use which technology at this time more effectively. So whenever we are doing any part of our work, we can see, okay, these are the possibilities for using technologies. This is the relevance of these technologies in future-proofing the structures. So if we want to ensure serviceability, safety, resilience, flexibility, adaptability, these technologies can also help us or can play some part. So combining our structural design process and the future-proof awareness, we can bring in technologies and integrate them into our work with a conscious effort to make the structures future-proof. I'll give you a couple of examples from our work in AIT. This is, for example, one work in which we integrated many technologies together, drone, 3D printing, finite element analysis, wind tunnel, many things together to design a dome for a large sort of space. We don't have the time, but I'm just giving you an example where integration of technologies can really help to come up with good solutions. BIM is one of the technologies that I think none of us can ignore anymore. And unfortunately, structural engineers are slow to adopt this. Architects are much ahead of us. Other disciplines, mechanical engineers, MEP engineers, they are ahead of us. In the entire building industry, we are the last one. Structural engineers are probably lagging behind all of the others, unfortunately. So civil engineers, structural engineers, we need to embrace BIM as a basis of managing project lifecycle information and everything. And I can give you just one example that BIM actually can integrate a lot of information about the structures, about the infrastructure, and it can, more importantly, point it to a relevant physical entity. So we can link the information to physical entities, and that's the key, that we have a relevance of the data to physical entities, and that makes all the difference. So all the data sheets, they basically link to something that you can capture, you can think about, or you can physically manage. So that's why connecting BIM to our work process is very important. And as you know, those of you who are involved in BIM, they know that the BIM has several dimensions. We used to talk about 5D BIM. Now 6D, 7D, and up to 10D BIM is already in development. So we are talking about BIM for not only shape and drawings, scheduling, estimating, sustainability, maintenance of structure, safety, for lean construction, and most importantly, post-construction hazards and other aspects. So everything is now integrated all the way through the life cycle using various dimensions of the BIM. At the same time, the level of detail in BIM is also increasing. From level of detail to 100, we are now at a level of detail of 700, which means extremely detailed information is now embedded in BIM models. At some point, we were very happy to have a 3D model. That is our level of detail of the structural element. Now you have structural elements, plus reinforcement, plus connection details, plus fabrication, plus all of those issues related to that. So combining the dimensions of BIM and the level of detail in BIM, we almost have unlimited capacity to manage this information and make use of this information in everything that we do. And in fact, this is one of the focus of our company, the one that we set up in Bangkok right now, CSibangkok, looking into BIM and integrating into civil and structural engineering. Next one, of course, is AI and machine learning. A few years ago, when I used to talk about AI and machine learning, people didn't really realize or recognize the significance of this one. But since ChatGPT, or since these large language models, since last November, the world has changed. And if we don't recognize that, then we are missing something. Because everything that we thought about the future is actually here. This last few months, the change of adaptation of AI in everything is absolutely mind-boggling. We cannot even keep track of what's happening. So AI is absolutely now here, finally, in the sense that there have been a couple of times that AI came and went and came and went, but now it seems that now is finally here. So using AI, we can do a lot of things. For example, we can do quick decision making, estimating. Like, for example, normally we have the design process in a step-by-step, from architect to planability to structure to analysis and so on. But using AI, we can simply jump from the architectural design to code-based design directly, for example, or to performance-based design, because we can train our models based on the work that we do. So we can skip all of the work and go directly to the end results, and we can predict that. Now, those of you, I'm sure everyone here is familiar with ChatGPT or similar large language models. So right now, as engineers, and I'm sure you have heard about the prompt engineering, the new discipline coming up, self-created. There is no such discipline. People have just started to call themselves prompt engineers, and people are making a lot of money by writing in their CV that I'm a prompt engineer and getting paid. Basically, what it means is how to interact with AI. So if you have the ability to interact with AI, with the large language models properly, you already have an edge over the others. And as engineers, we definitely need both the ability to create the prompts and also to create these large models for our own discipline, so that our work also becomes part of this AI. You can call it evolution or whatever you want to call it. But it is definitely something that is absolutely sweeping across every discipline. Things are changing so fast that it's unbelievable. Then we also have the generative design, which is very much related to future proofing as well. And it is the extension of the iterative design, but in a more controlled manner, where we combine parametric, generative, and AI into integrated design methodology that by itself finds the right solution for the problem. And this is, once again, architects are way ahead of us. Zaha Hadid, I think you most might have heard her name, the famous architect. Unfortunately, he passed away a few years ago. And she's the architect of most of the buildings in Dubai. So she was really, really a front runner in using generative design to create her structure, her buildings, which were both architecturally and structurally integrated right from the beginning in the form. So generative design, and I'll give you just very quick example of what can be done. For example, if you want to design a bridge pier and you want to size the cross-section with considering aesthetics and the golden rule of proportion, and you want economy and formwork and everything, you could create a parametric generative model and go through various variations very rapidly through this generative design process until we find the solution that we are looking for. So basically, it's a parametric design which looks at all of the realistic variations of parameters until it finds the solution that we find acceptable. And we can extend that to, for example, even the reinforcement inside. So as you change the form, the reinforcement also can be adapted, and then we can find the quantities and the capacity and everything at each cycle. So the generative design can not only look at the form, but can also look at the cage inside at the same time, which means look at the capacity, look at the performance, and look at everything, so we can complete the entire cycle. So, for example, this could be used to come up with the most beautiful or economical or efficient design of a bridge pier, as a small example. Big data, another one, because everything, as you know, is about data. There's more data now in one day than there was all in history before that. So we need to be aware there is some value in this. Companies are built, businesses are built on using data at this time. And we as structural engineers, civil engineers also need to make use of that for our projects, for our work and our profession. Sensing technologies, once again, it is very, very important that we use sensors effectively in our structures because they provide a lot of opportunity for monitoring of what is going on, short term as well as long term. And together with the IoT, we can have a lot of information. Sensors have become so cheap that it is unbelievable. As you know, everyone knows that our cell phone has all kinds of sensors, including the acceleration sensors and temperature sensor, humidity, whatever. So about 25, 30 sensors are built in, which we could always access for doing a lot of work. Blockchain-based applications, we can connect things to what's happening. We can document them. We can create the ownership. So blockchain itself, big data blockchain themselves have provided us a lot of opportunity to actually manage our work in a very, very controlled manner. And already other businesses are using it. And as engineers, we also can make use of these technologies. Drones, we all are fascinated by the drones and the images created by drones, the models created by drones. They can help us in a lot of things. In fact, I was quite surprised that one of our papers that we published a few years ago on using drone for construction management received about 10 times more readership than our papers on structural design. It seems that people are much more interested to read about the application of drones to construction than application of structural engineering and performance-based design, for example. So this is an area which everybody wants to use that. 3D printing is related to all the other technologies together. IoT, once again, sensors, IoT, structural health monitoring, they're all part of the same big equation. And then we have the convergence in terms of the cell phone, where we can bring all of these things together because everything that we do, we can connect it, or we can either control it, or we can bring it back to this device. And we have the smart cities on a larger scale where everything converges. So it's a convergence of planning, engineering, technology, management, mobility, engineering, energy, retail, everything. So smart city, the way we look at it a different way, is actually a culmination of everything that can bring together, because every discipline, every technology has to come together in an integrated manner to create so-called smart city. So I have a few slides about what we are doing about this at AIT. This portion, I want to go into slight depth of some of these areas because many ideas we touched upon, but we didn't actually show examples of how it can be done and how it is done. So I want to show some of the research done at AIT by our group on some of these applications so we can see some examples, and then maybe we can see that what we're talking about is not just only talk, but actually it is applicable. So first of all, the design, development and future-proofing in AIT, mostly we are working a lot on performance-based design, risk-based design, resilience design. We don't do much work on code-based design, but we do a lot of work on the other part of the design process. So that I just want to emphasize that's the focus of AIT's current work is on performance-based design, risk-based design, and resilience-based design, and obviously future-safe design. Second one is the application of technologies, and we are looking at many, and this is some of the elements where you see dark green color, that is where we are doing more work, and light green color where we are not doing a lot of work, and we hope that we will be doing that in the future. So you can see here a lot of work on virtual reality, mixed reality, augmented reality, data analytics, AI, IoT, drones, some of robotics, and so on. So now I want to give you some examples of some of the thesis, some of the research, some of the projects in this area, so we can now understand how this could be relevant, or how some of that could be done in our own universities in Pakistan. So once again, the relevance of our work with the future proofing. So let's see, first of all, this is a thesis done by one of the students using data analytics approach to estimate the efficiency of the structural design of tall buildings. Because when we talk about future proofing or all of that, we have to look at efficiency as one of the indicators. So how do you define efficiency? What is an efficiency? And how can we determine efficiency through data that we have collected. So this is basically focuses on, first of all, defining the efficiency parameters, and then defining a way to evaluate efficiency, and then defining a way to compare efficiency between various types of structural system and structural members. So this research is quite useful because it helps us to explicitly think about data and efficiency and how we can compare two structures in terms of their efficiency in various aspects, including climate change and including sustainability. This is, which is by Ashish, who's actually joining this talk also. He is looking at the calibration of structural models using measured building response. So that's another area that we try to do a lot of work, that we measure the response of the actual buildings and bring it back to the models of a building and calibrate them so that because when we create a model, we do the design, we don't know how accurate that is. We only have an idea of what we are doing. But if we can also go back and measure the response of the building in use and bring that information back and then calibrate the models so that the models predict the same response as we measured, that means we have removed the modeling errors in our structures. So modeling assumptions, modeling inaccuracies, those can be removed or minimized by recalibrating the structure based on the measurement of the same structure in operation using sensors. And we have been connecting this research to some buildings in Philippines where sensors have been installed. And this is done, by the way, in bridges quite a lot. Bridges are the biggest application is in bridges, and a lot of our other colleagues are working also in doing the same thing with bridges. Then another one we did using image-based inspection and monitoring of tall buildings. That means if you just take a picture of surface or a building, then based on that picture, we should be able to determine where it is cracked and what that crack means. Is it a flexural crack? Is it a shear crack? Is it important? Is it dangerous? It's not. So basically taking images, either through drones or through cameras, we can bring that back images. We can identify the cracks. We can find the crack width. We can find the crack length. We can find the crack direction, crack pattern, number of cracks. And from that, we can start to see whether the structure is deteriorating or not. And once again, as I mentioned, this is related to future proofing in the sense that maintenance and durability and structural health can be measured, can be evaluated without actually going near or measuring. So this is by taking pictures from far and using various techniques to basically determine the state of the building. Right now, this is focused on cracks. And then he was able to do that, identify crack width, crack angle, determine whether it's a shear crack or it's a flexural crack, and so on. So this is combined the technology of imaging and the image analysis with structural performance. Another one is quite important, this thesis on enhancing seismic resilience of non-structural members in buildings. Many times as structural engineers, we are focused on the structural members, the safety or the performance of the structural members, beam and column and so on. But in reality, most of the time, the damage first goes to non-structural elements. Walls, partition walls, floors, ceilings, glass panels, and so on. And that damage is actually far more severe to buildings, operations, and occupants than the structure itself. Those of you who have seen the videos from Japan for earthquake, basically it's the thing falling down with the walls cracking, but the structure is intact. But the building is destroyed. So this is connected to using the structural information to determine the non-structural damage and link that to resilience and to resilience design and to the buildings linked to the recovery of the building and so on. So this is quite an interesting work. In fact, we are connecting that to the analysis and design, so this can be automated to some extent. This is the use of artificial neural networks or AI for the analysis of highway overpass bridges and so on. So there are several theses that we have done looking at the application of AI on various types of structures, bridges, bridge piers, buildings, and so on. Once again, training the networks based on the available data or by generated data. Another one is structural health assessment of post-earthquake response to all building. This is a project that we are doing in Philippines where many buildings are being connected together because by law, every building in Manila, in Philippines, must have accelerometers. So accelerometers are attached, but their data is not going anywhere. So we are trying to connect that data, extract that data, and take that data, connect it, and network it so we can predict the damage to the city after an earthquake. Not only damage, but what is the impact of the earthquake even before inspecting, because we can correlate it back to the model and so on, like I mentioned, calibration and so on. So this is quite a large initiative. We're trying to work with developers, with the authorities to bring this into operation, but there are many practical considerations which are becoming difficult. But technology-wise, we have already completed this solution. So this is the sort of block diagram where you have the buildings where we have sensors and they are triggered sensors when there is an event or earthquake, and then we have the data collection and so on. And finally, the information goes on a mobile phone to the owners or to the occupants that what happened to the building after an earthquake. Without doing an inspection, we can sort of assess that there's going to be a crack in a shear wall at that floor. So that's the level of detail we are looking at. This is a project we did in Pakistan a few years back with Alvin Foundation. This is Baltic Fort. Those of you who have a chance to go there, it's a beautiful place to go. I actually went there myself together with my team. And then we did the drone imaging of so the objective was to determine the seismic vulnerability of this old fort. And then the drawings are not available and measurement is not possible. So we did the drone imaging to create a drone model. From that, we created a BIM model. From that, we created a SAP model. And from that, we created a finite element model. And then we were able to analyze it. So without taking any physical measurement, only using drone imaging and internal scans, we were able to create reasonably good structural model that could be used for stress evaluation of this structure. So once again, integrating many technologies together into this one, drone imaging and photogrammetry and BIM and so on. This is another project that I mentioned to you, received a lot of interest in terms of the publications, in which we tried to monitor the construction through using drones and compare the construction progress with the BIM model. Because if you take a drone image of a construction site and you can create from that a 3D model, and then you also have a BIM model as to be constructed, then we can overlay those BIM models and the drone model, and then you can find what has been constructed, what is discrepancy, what is missing, and so on. So you can actually do a progress monitoring without doing any physical measurement by only using drone imaging. This is difficult in practice because many tall buildings, especially, they are covered by these screens during construction. Inside, you cannot access. So it's more suitable for bridges and roads and tunnels and drainage systems than for buildings. But this is a very valid way of doing construction monitoring, progress monitoring. Then there is this integrated digital delivery system, which is beyond just analysis. And this is a project with Singapore that we are doing. The Singapore government has a project called COT, Cities of Tomorrow. And one of that is to use this digital delivery system. That means everything should be digitally done and delivered. No drawings anywhere in the process, no printed drawings to be signed or delivered, only digital information transfer between all stakeholders right to the construction. And that is this digital, and we are part of that project, that we are also developing some tools in that big project. So having talked about all of that, we should not forget our own profession. Because as professionals, structural engineers, I think we are pretty conservative compared to many other disciplines. And when we interact with many people, we realize that our profession also needs to future-proof itself so that we don't lose this profession in the future. Although it is very encouraging for us to see that in this year intake in AIT, structural engineering program has the highest number of enrolled students compared to all other disciplines, including all engineering, non-engineering combined together. So structural engineering seems to be still of interest to students. So we have the largest number of students enrolled this year. But to keep that, we need to embrace new technologies, as I mentioned, also think about sustainability and resilience, lifelong learning, interdisciplinary collaboration. We have to make sure, when we go to a meeting, in a project meeting, we always see that architects or town planners, they lead the meeting. Engineers are left behind. We have to have more input or we more say in this process. Adaptable design development, regulation and standard development, public engagement, communication, we lack that a lot. I think we all know that when it comes to public engagement and communication, we lag behind many other disciplines. And obviously, ethical considerations, all of that is something that as a profession, we should be looking at. And future-proofing our own careers, which is an extension of the profession. But once again, continuous learning is key. Technological adaptation, once again, is very important, like I mentioned. A soft skill development. And once again, a weak point in engineers. Our soft skills are not as sharp or as soft as they should be. And if you look at job requirements, go to internet and say, what are the top 10 job requirements? You will find soft skills to be top 1 or 2, communication skills to be high. In fact, I remember one time I met somebody who was interviewing engineers, and he said, even Einstein, I would not take if the attitude and the soft skills are not good. If they cannot work together in a team, we don't want, even if they're very, very smart. So that's the kind of the attitude these days. Networking is also important, but obviously specialization is still relevant. Each one of us has to be specialized in some area. Sustainability focus in everything that we do. And once again, adaptability. And the last one is quite important, entrepreneurship. Having this business setup mind or creating jobs rather than finding jobs. I think structural engineers are pretty good at this one. Many people open their own companies very quickly. I can see Rizwan is here, I'm here. Many of us, we did that when we finished graduation. We started our own business, our own companies, and provide employment rather than seek employment. So that entrepreneurship is actually pretty much there, but something that we need to further probably formalize. So these days, there's a lot of talk about robots and AI taking over jobs. And there is a website that you can go and check whether your discipline will be taken over by AI or robots. It's just a lighter side of the discussion, nothing to be. So if you go there and you say that accountants and auditors, 95% chances that their job will be taken over by AI very soon. So basically, this profession, according to that website, is doomed. If you look at computer programmers, they have to start worrying. And that is so true. ChatGPT, Copilot, so many tools have come that simply do the programming almost automatically. And if you are following ChatGPT kind of things now, it can write the program for you, even if you have no programming experience. Just define the problem and the program comes out all done, nicely written, pretty good. So programmers have to start worrying about their job and their discipline because AI is clearly taking over that. Civil engineers totally safe at this point. According to the website, the civil engineering and structural engineering is still very little chance that we will lose our job because we have a lot of things that still need human and interaction and so on. But it all depends on if we keep ourselves relevant, like I mentioned before. Thank you very much.